Welcome to this coding walkthrough. In today's session, we'll be tackling LeetCode problem number 1085, titled Sum of Digits in the Minimum Number. This is a straightforward yet interesting problem that challenges our ability to work with arrays and digit manipulation efficiently. Let's dive in and explore the solution step by step. In this problem, you are given a list of positive integers called nums. Your goal is to identify the smallest number in the list and calculate the sum of its digits. Once you have the sum, you need to determine whether it is odd or even. If the sum of the digits is odd, the function should return 0. However, if the sum is even, the function should return 1. For the input format, the list nums is guaranteed to be non-empty, and every number in the list is a positive integer. The output is a single integer, which will either be 0 or 1 based on the parity of the digit sum of the minimum number. Let's look at some examples to understand how this works. In the first example, the input list is nums equals 34, 23, 1, 24, 75, 33, 54. Here, the smallest number in the list is 1. The sum of its digits is simply 1, and since 1 is odd, the output is 0. Now in the second example, the input list is nums equals 99, 77, 33, 66, 55. The smallest number in this case is 33. To find the sum of its digits, we add 3 plus 3, which equals 6. Since 6 is even, the output is 1. These examples highlight how the function decides between returning 0 or 1 based on the parity of the digit sum. Let's consider one more example for clarity. If the input list is nums equals 50, 40, 30, 20, 10, the smallest number is 10. To find the sum of its digits, we calculate 1 plus 0, which results in 1. Since 1 is odd, the function should return 0. This process works for any list of positive integers by consistently identifying the minimum number, calculating the sum of its digits, and checking whether the sum is odd or even. The constraints ensure that the list will always contain at least one number, each number will be positive, and the list can have up to 100 elements, making the problem manageable within these limits. When implementing the solution, it's important to consider edge cases. For instance, if the list contains only one number, like nums equals 7, the function should return 0 because the sum of the digits of 7 is odd. If all the elements in the list are the same, such as nums equals 11, 11, 11, the function must still compute the digit sum of the minimum value, which is 2, and return 1. Another scenario is when all numbers have the same digit sum but different values, like nums equals 21, 12. Here, the minimum number is 12, and the digit sum is 3, which is odd, so the output is 0. Lastly, for a list with up to 100 numbers, the function must efficiently process the input and determine the result without exceeding time limits. These considerations ensure the solution is robust and handles a variety of inputs correctly. To solve LeetCode problem number 1085, we need to calculate the sum of the digits of the smallest number in the given list, nums, and determine if the sum is even or odd. If it's even, we return 1, otherwise, we return 0. One straightforward way to approach this is the brute force method. The intuition here is simple. First, we find the smallest number in the array by iterating through all the elements. Then, once we have the minimum value, we calculate the sum of its digits. This can be done by repeatedly using modulo to extract the last digit and integer division to remove it, until there are no digits left. Finally, once we have the sum of the digits, we check its parity. If it's even, we return 1, if odd, we return 0. This method is clear and effective, but it involves separate loops for finding the minimum and summing the digits, which might leave room for optimization. When analyzing the complexity of the brute force approach, we find that the time complexity is O(n) for traversing the array to find the minimum, and O log min_value for summing the digits of that minimum value. Overall, the time complexity is O(n). The space complexity is O(1), as no additional data structures are required. However, while this approach is efficient, it has a drawback. The tasks of finding the minimum and calculating the digit sum are performed in separate loops. This means that the process could potentially be streamlined further. To address this, we can consider an optimized approach that combines these tasks into a single loop. The optimized approach starts with initializing a variable to track the minimum value. As we iterate through the array, we constantly update this minimum value and calculate the digit sum simultaneously, allowing us to complete the task in fewer steps. This eliminates the need for separate iterations and makes the process more efficient. Another potential approach is to use sorting to find the smallest number. By sorting the array in ascending order, the smallest number is guaranteed to be the first element. Once the array is sorted, we can directly compute the digit sum of this first element and determine the parity of the sum. While this approach is conceptually straightforward, it is significantly less efficient than the others. Sorting the array has a time complexity of O(n) log n, which is much higher than the O(n) complexity of the previous methods. Additionally, sorting introduces unnecessary overhead, as we do not need to process all elements in the list, only the smallest number matters. While this method works, it is not well suited for this problem due to its inefficiency. The optimized approach is the best choice for this problem because it strikes the perfect balance between simplicity and efficiency. It avoids the unnecessary overhead of sorting the array, as seen in the alternative approach, while combining the tasks of finding the minimum and calculating the digit sum in a single traversal, unlike the brute force method. The key insight here is that only the smallest number in the array affects the result, so all other elements can be ignored. By iterating through the array once, we can identify the minimum value and compute its digit sum simultaneously, achieving O(n) time complexity with O(1) space. While it is technically possible to calculate the digit sum directly during the traversal, separating the two steps makes the solution more intuitive and easier to understand. In comparison, the brute force method uses separate loops, which makes it slightly less efficient, and the sorting approach, with its O(n) log n complexity, is overkill for such a simple task. Therefore, the optimized approach is the clear winner, offering a clean and efficient solution to the problem. In this problem, we are tasked with solving LeetCode number 1085, titled Sum of Digits in the Minimum Number. The goal is to determine the sum of the digits of the smallest number in a given array, and based on this sum, return 1 if it's even or 0 if it's odd. Let's break it down step by step. First, we need to understand the input and output. The input is an array nums containing integers, with some constraints. The length of the array is between 1 and 100, and each number in the array is between 1 and 10,000. The output is a single integer, either 1 or 0. The first step in solving this problem is to find the minimum number in the array. We can do this easily in Python using the min function, which scans the array in O(n) time to find the smallest value. For example, if the input array is 34, 23, 12, 45, the minimum number is 12. Once we have identified the minimum number, the next step is to calculate the sum of its digits. To do this, we extract the digits one by one using a loop. Start by initializing a variable digit underscore sum to 0. Then, use a while loop to repeatedly extract the last digit of the number using the modulus operator, %10. Add this digit to digit underscore sum, and then remove the last digit from the number using integer division, //10. Keep repeating this process until the number becomes 0. For example, if the minimum number is 12, we first extract 2 and add it to digit underscore sum, making the sum 2. Next, we extract 1 and add it to digit underscore sum, bringing the total to 3. Once the digits are summed, we move on to determine whether the sum is even or odd. This is done using the modulus operator again. If digit underscore sum %2 equals 0, the sum is even, otherwise, it is odd. In our example, 3% equals 1, so the sum is odd, and we return 0 as the result. Now that we've covered the steps, let's highlight some key insights about the algorithm. First, finding the minimum number using the min function is both simple and efficient, as it avoids manual iteration. Next, the process of extracting digits using modulus and integer division is a straightforward and efficient way to compute the sum of digits. Finally, checking whether a number is even or odd with the modulus operator is a constant time operation, O(1), which ensures this step is highly efficient. In terms of data structures, this problem does not require any additional structures since we operate directly on the input array and use a few integer variables, making the space complexity O(1). For time complexity, finding the minimum number takes O(n), where n is the length of the array. Summing the digits of the minimum number takes O(k), where k is the number of digits in the smallest number. Since k is at most 5 for the given constraints, the overall time complexity is O(n). To ensure the robustness of the solution, we should consider some edge cases. First, if the array contains only one number, the algorithm still works because that number is the minimum. Second, if all numbers in the array have the same value, the approach naturally handles this by calculating the digit sum of the repeated value. Lastly, even with large numbers up to the maximum limit of 10,000, the algorithm remains efficient because the number of digits is capped at 5. Let's walk through an example to solidify our understanding. Suppose the input is nums equals 34, 23, 12, 45. In step 1, we find the minimum number, which is 12. In step 2, we calculate the sum of its digits. We extract 2 and add it to digit underscore sum, resulting in 2. Then, we extract 1 and add it to digit underscore sum, making the total 3. In step 3, we check if 3 is even or odd. Since 3% 2 equals 1, the sum is odd. Finally, in step 4, we return 0 as the result. The output for this input is therefore 0. This Python solution solves LeetCode problem number 1085, sum of digits in the minimum number, efficiently and concisely. Here's the detailed explanation of the code. 1. Finding the minimum number. The function min, nums, is used to find the smallest number in the input list nums. This takes O(n) time, where n is the length of the array. 2. Summing the digits. The smallest number min underscore number is converted to a string so that its digits can be iterated over. Using a generator expression inside the sum function, each digit is converted back to an integer and summed up. This process effectively calculates the sum of the digits of the smallest number. The complexity of this step depends on the number of digits in the smallest number, which is bounded by the constraint, numbers up to 10 to the power of 4. 3. Checking parity. The result of the digit sum modulo 2 determines if the sum is even or odd. If the result is 0, even, the function returns 1, otherwise, it returns 0. This step is O(1). For edge cases, the code robustly handles cases where the input array has a single number, or all numbers are the same, or the smallest number is a single-digit number. This implementation is efficient with an overall time complexity of O(n), where n is the size of the input array. The space complexity is O(1), since no additional data structures are used. The function adheres to the problem constraints and provides a clean, production-ready solution. This is the Java implementation of LeetCode problem number 1085, sum of digits in the minimum number. The logic mirrors the provided Python solution. Key differences include the use of Java's arrays.stream to find the minimum value, and a while loop to calculate the sum of the digits. Java's type declarations and syntax are used for clarity and correctness. The method returns 1 if the sum of the digits is even, otherwise 0. To solve the problem, we begin with the array 34, 23, 45, 12, 9. The first step is to find the smallest number in the array, which is done using the min function. In this case, the minimum value is 9. Next, we calculate the sum of its digits. Since 9 is a single-digit number, converting it to a string still gives 9, and the sum of its digits is simply 9. The final step is to check whether this sum is even or odd. We do this by checking the remainder of digit underscore sum when divided by 2. Since 9% 2 equals 1, the sum is odd, so the function returns 0. The final output for this example is 0. Now, let's look at the next example with the array 10, 20, 30, 40, 50. Again, we start by finding the smallest number in the array using the min function. The minimum value here is 10. To calculate the sum of its digits, we convert the number 10 to a string, resulting in 10. The digits are 1 and 0, and their sum is 1 plus 0, which equals 1. Next, we determine whether this sum is even or odd. Since 1% 2 equals 1, the sum is odd. Therefore, the function returns 0. The final output for this example is also 0. In the third example, the array is 8, 16, 24, 32. The smallest number in this array is 8, which we find using the min function. To calculate the sum of its digits, we convert 8 to a string, which is 8. Since 8 is a single-digit number, the sum of its digits is simply 8. Finally, we check whether this sum is even or odd. This time, 8% 2 equals 0, so the sum is even. As a result, the function returns 1. The final output for this example is 1. In summary, the solution involves 3 steps: finding the minimum number in the array, calculating the sum of its digits, and determining whether that sum is even or odd. For the given examples, the outputs were 0, 0, and 1, respectively. By breaking the problem into these simple steps, we can systematically solve similar questions efficiently. This approach highlights the importance of combining basic operations like finding a minimum, iterating over digits, and using modular arithmetic to solve problems in a structured way. When analyzing the time complexity of the function sum of digits, we can break it down into 3 key steps. First, the function identifies the smallest number in the array using the min function. Since this operation requires iterating through all elements of the array, it takes n time, where n is the length of the array. Next, the function converts this minimum number into a string and processes its digits. The string conversion and digit processing steps depend on the number of digits in the minimum number, which we denote as k, converting the number to a string, iterating through its digits, and summing them each take k time, so these combined operations also contribute k to the total time complexity. Finally, the function checks if the digit sum is even, which is a simple modulo operation and takes constant time, 1. Now, when we combine these steps, the overall time complexity becomes n plus k. Here, the n arises from finding the minimum number, and the k comes from processing its digits. However, in practical scenarios, the number of digits k is typically small and bounded by the maximum value of the numbers in the array, making it effectively constant. As a result, the time complexity simplifies to n. Next, let's consider the space complexity. The function uses space for storing the minimum number, which requires 1 space. Converting the minimum number to a string temporarily uses k space, as the string's length corresponds to the number of digits. Additionally, summing the digits creates an iterator, which also uses k space temporarily. Apart from these, other variables like digit_sum and the result only need 1 space each. Therefore, the total space complexity is k, but since k is small in most cases, it simplifies to 1. To understand the efficiency of the current implementation, let's compare it to a brute force approach. A naive method might involve calculating the digit sum for every number in the array and then identifying the smallest number with an even digit sum. This approach would require multiple passes through the array, leading to a time complexity of n*k, where k is the average number of digits per number. In contrast, the optimized implementation significantly reduces operations. By focusing only on the smallest number in the array, the digit sum is calculated just once, bringing the time complexity down to n. This improvement demonstrates how narrowing the scope of computation can drastically enhance performance. Finally, let's analyze the best, average, and worst-case scenarios for the function. Regardless of the input, the time complexity remains n in all cases. This is because the function always needs to iterate through the array to find the minimum number, and processing the digits of this minimum number involves constant time relative to n. The number of digits in the minimum number, k, does not depend on the size of the input array, so the function's performance is consistent. In conclusion, the algorithm is both efficient and predictable, with a time complexity of n and a space complexity of 1 under typical constraints. This makes it well suited for the problem at hand. When working on this problem, there are a few common mistakes to watch out for. First, ignoring edge cases can lead to unexpected behavior. For example, if the input list is empty, you need to clarify whether the function should return a default value or throw an error. Similarly, if there's only one number in the list, ensure your logic still holds. Another mistake is accidentally using max nums instead of min nums, a simple oversight that can occur when copying or editing code. Additionally, errors in calculating the digit sum are frequent. Instead of converting the number into a string and summing the characters, which results in string concatenation, you need to convert each digit back into an integer before summing. It's also important to respect the input constraints. If the problem specifies that all numbers are positive integers, there's no need to add unnecessary checks like verifying if a number is negative. Finally, watch out for off-by-1 errors in your parity logic. For instance, if the goal is to return 0 for odd and 1 for even, mistakenly returning some %2 instead of 1, some %2 can lead to incorrect results. These small details can significantly affect the correctness of your solution, so double-check these areas as you code. Now, let's talk about key insights that can help you approach this problem effectively, especially in an interview setting. The core of this problem lies in modular arithmetic and efficient list processing. Using min, nums, to identify the smallest number ensures that you minimize operations and avoid redundant computations. From an optimization perspective, the time complexity is straightforward. Finding the minimum value in the list takes O, n, and summing the digits of the minimum number depends on the number of digits, which is O, log, min underscore number. Together, this ensures your solution is efficient. During interviews, it's just as important to communicate your thought process clearly. Explain how you handle edge cases and clarify any assumptions, like asking the interviewer if the input list could be empty. Be prepared for follow-up questions as well. For instance, you might be asked how you would extend the solution to calculate the digit sum for all numbers in the list or to return the sum directly instead of its parity. Finally, recognizing related problems can deepen your understanding. For example, LeetCode number 7, reverse integer, also deals with digit manipulation and edge cases. LeetCode number 258, add digits, focuses on summing digits, while LeetCode number 66, plus 1, and LeetCode number 1281, subtract the product and sum of digits of an integer, involve similar operations on digits. Drawing these connections can help you see common patterns and refine your approach. There are also alternative approaches you can explore to solve this problem. One option is to iterate through the list manually to find the minimum value instead of using the built-in min, nums. While this makes the code slightly more verbose, it gives you full control over the implementation and may be preferred in environments where built-ins are restricted. Another interesting variation involves summing the digits recursively instead of iteratively. While recursion can improve conceptual understanding, it's less efficient due to extra stack space usage and may not be ideal for large inputs. A third alternative is to employ branchless techniques for parity calculation. Instead of using conditionals, you can directly compute the result using modular arithmetic, such as 1 digit underscore some %2. This reduces branching in your code, which can be beneficial in certain scenarios, though it might make the solution less readable for some developers. Each of these approaches has trade-offs, so understanding their strengths and limitations can help you decide which one is most appropriate for the context or constraints of the problem at hand. Great job! We've successfully solved LeetCode problem number 1085, sum of digits and the minimum number. We explored the problem, broke it down into manageable steps, and implemented an efficient solution. Remember to focus on clarity and edge cases when solving similar problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!